Hey guys, we're going to talk about acids and bases today. Now, some of this sort of foundational information you probably know from 8th grade, but a lot of the math, if not all of the math, is going to be new to you. So if you're struggling with it, please don't worry about it. When we have our in-person session, we're definitely going to go through how to do these calculations. That'll probably be our main focus because as far as the properties of acids and bases go, it'll be very easy to get those from this video lesson. Okay, so I want you to read through these 8 things and see if you know which of those things apply to acids and which apply to bases. And we'll revisit this at the end once we've been through everything and talk about which is which. Now, my guess is you probably know which one has a pH greater than 7. You probably know which one feels slippery and tastes sour, and you should know 7 and 8 from Unit 5 when we talked about neutralization reactions, but you may not be so sure about 1, 3, and maybe 4. Okay, so let's go through and talk first about some properties, and then we'll talk about some of the math associated with pH. And so when we talk about the properties of acids and bases, first we might talk about how they feel if they were to get on our hands. Now, obviously in a lab, we want to take precautions to make sure that doesn't happen, but there are also acids and bases in your home. Okay, so if you've ever had like a cut on your hand and got lemon juice in it, you know that acid burns a little bit. And bases feel slippery. So soaps are bases. So if you had a base even in the lab, like sodium hydroxide, and you got a little bit on your hands, it would feel like you had soap on your hands. Now, there are acids and bases that we eat. Obviously, we don't eat lab chemicals, but edible acids taste sour and bases taste bitter. And as far as their reactions, acids have a very characteristic reaction with metals. They produce hydrogen gas, whereas bases have no particular reaction with metals. Now, when we talk about litmus paper, you probably use this in 8th grade, and I might actually try to make some of my own pH paper at home, so we'll see if I can manage that. But litmus paper turns red in the presence of acid and blue in the presence of base. You can remember that because base blue, acid red, I don't know. Acids have a pH of less than 7 and bases have a pH of greater than 7. Now, phenolphthalein is the most common indicator that we use, at least in classroom labs. And if we were in school together, we would do a titration with phenolphthalein as an indicator. And phenolphthalein is clear in acid and pink in base. Now, solutions of acid and base both conduct electricity. And the reason they conduct electricity is that they dissociate into ions when they're in water. So because there are ions present, they will act as electrolytes. So let's talk about some definitions. There's actually multiple definitions of acids and bases. The sort of most common one that you're very familiar with are the Arrhenius definitions. And in this definition, we say that an acid is something that produces hydrogen ions and a base produces hydroxide ions. And this is specifically in water. Now, this is how we most often recognize these. It's a very functional definition, right? Because it's very easy to look at something and say, oh, that starts with H, it's probably an acid. Oh, that ends in hydroxide, it's probably a base. Now, in water, the hydrogen combines with water to produce something called the hydronium ion, H3O+. So we tend to sort of use H+ and H3O+ interchangeably because that's how H+ really exists in water. Now, the limitation of this definition is it's only applicable in aqueous solutions, okay? And plenty of reactions happen outside of aqueous solutions. So we have a broader definition that we'll talk about in a second. Mostly, when we talk about things in class, we'll be working with aqueous solutions, so this is a very applicable and useful definition, even if it isn't the most broad. The next definition is Bronsted-Lowry acids and bases, and this is broader. In this definition, an acid is a hydrogen ion donor and a base is a hydrogen ion acceptor. Okay, there is a third definition, Lewis acids and bases, and we talk about that in the upper level chemistry courses. You don't need to be familiar with that at this point. Now, I've mentioned phenolphthalein already and litmus paper, and these are examples of indicators. So an indicator is something that's a different color in an acid than a base. So some common indicators, litmus paper turns red in acid and blue in base. We also have something called variable pH paper, that there's a chart on the bottle that has a whole bunch of different colors that'll determine if it's an acid or a base. And I'm going to try to make a variable indicator at home that I can show you with some household things. And then phenolphthalein is a really common one that we use in the lab, clear and acid and pink and base. But there are so many indicators. This is just a snapshot of some indicators that we use. Okay, and they change at all different pHs, and they have all kind of different color changes. So one of the reasons that phenolphthalein is a really useful indicator, you can see it up here, is that it goes from colorless to colored. So that's a little easier to see than something that goes from, say, yellow to blue. That can be a little harder, right? Because there's that place in the middle where you're like, ooh, is that green? Is that blue? But colorless to red is really easy to see. All right, so let's talk about pH and something called pOH. I'm certain you've heard of pH before, but I'm not sure if you've learned about pOH, so we'll talk about that. Now, if we were to describe pH in the most simple way possible, we would just say it's a measure of the acidity of something, okay? Now, when we calculate the pH of something, the pH is the negative log of the hydrogen or hydronium ion concentration. Now, P is really just an operator that means negative log, okay? So pH is the negative log of H. Now, if we have the hydrogen ion concentration, we can solve for the pH using that equation. So pH is the negative log of the hydrogen ion concentration. So if we're given that concentration, all we have to do is on our calculator, take the negative base 10 log of that number, okay? And we would get 2.82 in this case. Now, sig figs with pH are a little bit weird because technically the only digits that are significant in pH are the ones after the decimal place. It's a little hard to explain via video lesson why that is. I'll try to address it during our class session, but realistically, don't worry too much about sig figs with pH. I'm not super concerned about that. Okay, and how can we calculate hydrogen ion concentration from the pH? Okay, so starting with that same equation, we're just going to rearrange it to solve for hydrogen ion concentration. So if you haven't done logarithms in math yet, this might be a little bit trickier, but I'm going to show you how all the log math works. But as long as you can use the equations on your calculator, it's all you truly need. So we can multiply both sides by -1, and then we can take 10 to the power of each side, and that will cancel out the log. So the hydrogen ion concentration is 10 to the negative pH. So if the pH is 5.6, we can also calculate the hydrogen ion concentration. So we can take 10 to the negative pH, which is 10 to the negative 5.6, but we don't leave a number like that. So we would just put that into our calculator and we would get 2.51 times 10 to the negative 6th. All right, so using those two equations, I want you to practice these problems. First, try to calculate the pH for those first two examples. And then for the second two, I want you to try to calculate the hydrogen ion concentration using the pH. So pause for a second and try those. And then when you're ready, you can hit play. Okay, so let's look at the first one. Now the hydrogen ion concentration here is 1.0 times 10 to the negative 3rd, okay? So that means the pH is 3, and I want to show you something sort of specific here. pH is the negative log of the hydrogen ion concentration, so it's the negative log of 10 to the -3rd. That's the same as 1 times 10 to the -3rd, right? Using log properties, I can take the -3 and put it in front of the log, okay? So then I get -3 times log of base 10. The negatives cancel out. The base 10 log of 10 is 1, so I just get 3. So if your hydrogen ion concentration is 1 times 10 to the negative something, that something is the pH, okay? Now, if that first number is anything but 1, then you have to actually put it into your calculator, but it saves you a little bit of time. All right, so here we have the hydronium ion concentration, which remember, we're basically using interchangeably with hydrogen ion concentration. And here, since it's not 1 times 10 to the negative something, we actually have to put this in our calculator. So we would take the negative log of that number, and we would get 10.13. Okay? So the first example, since the pH is 3, that would be an acidic solution. The second, since the pH is greater than 7, would be a basic solution. All right, so for the next two, we're calculating the hydrogen ion concentration. So the hydrogen ion concentration is 10 to the negative pH. So for the first one, it's 10 to the negative fifth, or 1 times 10 to the negative fifth. For the second one, we are actually going to put that in our calculator because we don't want to leave it as 10 to the negative 8.2. And we would get 6.3 times 10 to the negative ninth. Okay. Now, if you're having trouble with your calculator, figuring out where numbers are and which log to use and stuff, you can bring it to the office hours and turn on your video and I can help you that way. Okay, so let's talk about POH. Okay, so POH is the negative log of the hydroxide ion concentration. Remember how we said P was just an operator meaning negative log? Okay, so pH is the negative log of H. The POH is the negative log of OH. P elephant would be the negative log of elephant, okay? P just means negative log. All right, so we're gonna do these problems the same way. All right, so just for a second, pause and try to calculate the POH if the hydroxide ion concentration is 1 times 10 to the negative 6th. Okay, so again, we can do the same thing with log properties. We can take the negative 6 out front, and then negative 6 times base 10 log of 10 is just going to give us 6. You don't have to show out that work every time. I'm just showing it so you understand how it goes. All right, calculate the hydroxide ion concentration if the POH is 9. So just like we calculated the hydrogen ion concentration, hydroxide is going to work the same way. The hydroxide ion concentration will be 10 to the negative POH. So here it's 10 to the negative ninth. Now, you might remember from 8th grade that pH and POH have a relationship. pH plus POH equals 14. So if the pH is 6.8, the POH is 7.2. And to get that, I just take 14 minus 6.8. If the POH is 2.3, the pH is 11.7. Okay, I want you to try these two practice problems. Now, notice in the first one, I gave you the hydrogen ion concentration and asked you for the POH. In the next one, I gave you hydroxide and asked you to find the pH. So I want you to try at least the first one and then we'll go over it. And then we'll go over the second one as well. So pause for just a second. Now I want to show you that when we're looking at a problem like this, there's really 4 things that are kind of interrelated. We have pH, POH, hydrogen ion concentration, and hydroxide ion concentration. And sometimes people find it helpful in a problem like this to write those 4 things out. Okay, so I wrote those 4 things out and I wrote what I was given, which was the hydrogen ion concentration. Okay, now easily from that, I can find the pH, and the pH is 3, right? I could take the negative log of that number in my calculator, but since it's 1 times 10 to the negative third, I know the pH is just going to be 3. So if the pH is 3, the POH must be 11. Now to answer this question, you could just be done right there, but I'm feeling like an overachiever right now, so I'm going to go ahead and make sure I can find the hydroxide ion concentration. And remember, that's just 10 to the negative POH. So it'd be 1.0 times 10 to the negative 11. And now, if you couldn't get the first one before we went over it, I want you to pause now and try the second one. And if you've already done the second one, then you can just let this keep playing. Okay, so here we were given the hydroxide ion concentration, which is 1 times 10 to the negative 4th. So from there, we can easily figure out that the POH is 4. From there, then, we can figure out that the pH is 10, and if we wanted to, although we don't need to in this problem, we know that the hydrogen ion concentration is 1 times 10 to the negative 10th. All right, so just like pH and POH have a relationship, hydrogen ion and hydroxide ion concentrations have a relationship. And if you look at the sum of the exponents, you might notice that they're always going to add up to the same thing, and that's 14. So this relationship exists because of the dissociation of water. So even in totally pure water, some water molecules naturally dissociate or break up into hydrogen and hydroxide ions. Okay? Now, logically speaking, if all I have is pure water and some of it's breaking into hydrogen and hydroxide ions, the concentration of hydrogen ions must be equal to the concentration of hydroxide ions, right? Because every time I make a hydrogen, I also make a hydroxide. okay? And that concentration is 1 times 10 to the negative 7th. That's why the pH of pure water is 7. So these two things have a relationship. When I multiply them together, they're always going to equal 1.0 times 10 to the negative 14th, okay? And think about multiplying 1 times 10 to the negative 7th by itself, right? When we multiply things with exponents at the same base, we add the exponents. Okay, so I love log properties, and I'm going to show you why the pH scale is to 14 based on this. Okay, so we know from the last slide that the hydrogen times the hydroxide ion concentration is 1 times 10 to the negative 14th. Now, using log properties, I can take the negative log of both sides of the equation, right? As long as I do it to both sides, it's fine. Now, when I have two things multiplied together in the log, I can split the log, okay? And then on the other side, on the right side of the equation, I just simplified that by saying 10 to the negative 14th instead of 1 times 10 to the negative 14th. Obviously, they're the same. Now, the negative log of H+, we know another name for that. That's the pH. The negative log of hydroxide, we know another name for that. That's the POH, okay? And we can also take the negative 14 exponent and move it out front of the log. So now we have pH plus POH equals negative 14 times base 10 log of 10. The negative signs cancel out. The base 10 log of 10 is 1. So pH plus POH equals 14. Isn't that magical? I love that. Okay, so if you don't love log properties and you don't think that's magical, that's okay. I happen to love them, but again, you don't have to. All right, so let's look at an example problem that we can do with this information. And I'm not going to make you try to prove this, the pH scale is 14. That's just kind of for fun. We may have different definitions of the word fun, and that's fine. All right, so if the hydrogen ion concentration is 1 times 10 to the negative 10th, what is the hydroxide ion concentration? Now, there's a couple ways you could go about this, okay? You could use this equation and say from that the hydroxide ion concentration is 1 times 10 to the negative 4th. You could also use those four things that we talked about a couple slides ago. You could say, okay, well, the pH must be 10, so the POH must be 4, so the hydroxide ion concentration must be 1 times 10 to the negative 4th. All right, so the last piece of this is to talk about neutralization reactions. And we talked about these back in Unit 5, so this should mostly be review. This is when an acid and a base come together. And remember that this is just a special type of double replacement reaction. So the hydrogen and the hydroxide are going to combine, and the sodium and the chloride. And when they do that, we'll get water and sodium chloride. In the next example, same idea. Hydrogen and hydroxide come together, and magnesium and chloride come together. Now to balance this equation, I need a 2 in front of water, and I would also need a 2 in front of HCl, although I don't have that there. Pretend there's a 2 there, okay? So neutralization reactions are going to produce water and a salt. Now, we're going to use it, well, we won't actually be able to do this in person, but a really common technique that we're going to discuss is called titration. And in a titration, this is the technique that's used to find the concentration of an unknown acid or base by adding a base or acid of known concentration, okay? So we're going to use a piece of equipment called a burette, and this is like a really long skinny tube with lots of little markings, and this dispenses really precise amounts of liquid. So basically we would put our unknown in a flask here with a little bit of indicator, and we would put our known in the burette, and we would slowly drop it in until we had a color change, okay? And the color will change when the unknown is neutralized, okay? So we're going to use an indicator, which is going to change color, and once it's neutralized, the moles of acid equal the moles of base, okay? They're equivalent. So we can do a little bit of math from that. Okay, so since we know the moles of acid equal the moles of base, and we know that moles equal molarity times volume, if the moles of acid equal the moles of base, the molarity of the acid times the volume of the acid equals the molarity of the base times the volume of the base. However, the acid and the base don't always react in a 1-to-1 ratio, okay? So we're going to take this into account by looking at the number of hydrogens in the acid and hydroxides in the base. So the number of hydrogens times the molarity of the acid and the volume of the acid is equal to the number of hydroxides times the molarity of the base and the volume of the base. So let's look at one example together, and then I'll have you pause and do one on your own. All right, so what is the molarity of a potassium hydroxide solution if 25 milliliters of that solution is neutralized by 31.7 milliliters of a 0.1 molar nitric acid solution? Okay, so first we have to know what our acid and what our base are. Okay, now potassium hydroxide is our base, and the clue there is that it ends in hydroxide, OH. Okay, and HNO3 is nitric acid, that's our acid, and the clue is that it starts with a hydrogen. So I'm going to use my titration formula. Now, when I try to figure out the values for NH and NOH, I'm not going to look at any coefficients in the equation. I'm just going to look at the formula of the acid and the base. So when I look at the formula of the acid, there's only one hydrogen in it. Okay? When I look at the formula of the base, there's only one hydroxide. So in this particular example, NH is 1 and NOH is 1. Now, I know that the acid molarity is 0.1 molar, and I know that the volume is 31.7 milliliters. For the base, I'm trying to find its molarity, and I know the volume used was 25 milliliters. Now, you might be thinking that since molarity is moles per liter, that I should convert those milliliters to liters. That's really unnecessary because I would be dividing by the same thing on both sides. So as long as the volume units cancel out on both sides, it's fine to leave it in milliliters. And so when I solve this, I would get the molarity of the base is 0.127 molar. Okay, now I want you to try the second problem. Now remember, when you try to find the number of hydrogens and the number of hydroxides, be sure to look at the formula and not the coefficients. All right, so pause and try this and then we'll go over it. Okay, so again, we're going to use our formula. Now, when I look at the formula of the acid is H2SO4, sulfuric acid, and I can tell that because it starts with hydrogen. In that formula, there are 2 hydrogens, so the number of hydrogens will be 2. The base is potassium hydroxide. Looking at the formula, there's only 1 hydroxide. We're not going to worry about the coefficient of 2 there. Okay, so the number of hydrogens is 2, and we're trying to find the molarity of the acid. The volume of that acid is 25 milliliters. The number of hydroxides is 1. The molarity of the base is 1.00, and we use 27.4 milliliters. So the molarity of the acid would be 0.548. All right, so just to recap, phenolphthalein turns solution pink, it's pink in base. pH of greater than 7 is base. Reacts with metal to produce hydrogen gas is an acid. Turns blue litmus paper red is an acid. Feels slippery is a base. Tastes sour is an acid. Contains hydrogen ions is an acid. And sodium hydroxide is a base. Okay, there is a lot here. I acknowledge that, so please come with some questions and prepare to do some practice and get extra help in the class discussion.